Matter is anything that has weight or mass and takes up space. Even though it might not be obvious to us, all matter around us contains electricity in the form of positive and negative charge. Electric charges push and pull on each other over a distance. As we have discussed before, like charges will repel each other and unlike charges attract each other. Precise measurements of the forces on electrical charges were first carried out by the French physicist Charles Coulomb in the 1780s, using a device called a torsion balance, which measured the force generated between two electrically charged objects. The results of Coulomb's work led to the development of a unit of electric charge, named in his honor, the Coulomb. If two-point objects, hypothetical objects having no appreciable surface area, were equally charged to a measure of 1 Coulomb, which is the charge that flows through a 120-watt light bulb every second, and placed 1 meter, approximately 1 yard apart, they would generate an enormous force of repulsion of about 9 billion newtons, or approximately 1 million tons. In the 18th century, Benjamin Franklin proposed that electricity was a single fluid that could be transferred from one material object to another. It was discovered much later that this electric fluid was actually composed of extremely small bits of matter called electrons, so named in honor of the ancient Greek word for amber, the hardened sap from trees, another material exhibiting charged properties when rubbed with cloth. Experimentation has since revealed that all objects are composed of extremely small building blocks known as atoms, and that these atoms are in turn composed of smaller components known as particles. The three fundamental particles comprising atoms are called protons, neutrons, and electrons. It is believed by many physicists that protons and neutrons may be composed of even smaller structures called quarks. Atoms are too small to be seen with a microscope that uses visible light, because atoms are smaller than the wavelength of visible light. But they have been photographed by using beams of even smaller electrons. This is a picture of atoms in a metal crystal. Even though each atom in a piece of material tends to hold together as a unit, there's actually a lot of empty space between the electrons and the cluster of protons and neutrons residing in the middle of the nucleus. This crude model is that of the element carbon, with 6 protons, 6 neutrons, and 6 electrons. In any atom, the protons and neutrons are very tightly bound together, which is an important quality. The tightly bound clump of protons and neutrons in the center of the atom is called the nucleus, and the number of protons in an atom's nucleus determines its elemental identity. Change the number of protons in an atom's nucleus, and you change the type of atom that it is. In fact, if you could remove 3 protons from the nucleus of an atom of lead, you will have achieved the old alchemist's dream of producing an atom of gold. The tight binding of protons in the nucleus is responsible for the stable identity of chemical elements and the failure of alchemists to achieve their dream. Neutrons are much less influential on the chemical character and identity of an atom than protons, although they are just as hard to add or to remove from the nucleus, being so tightly bound. If neutrons are added or gained, the atom will still retain the same chemical identity, but its mass will change slightly and it may acquire strange nuclear properties, such as radioactivity. However, electrons have significantly more freedom to move around in an atom than either protons or neutrons. In fact, they can be knocked out of their respective positions, even leaving the atom entirely, by far less energy than what it takes to dislodge particles in the nucleus. If this happens, the atom still retains its chemical identity, but an important imbalance occurs. Electrons and protons are unique in the fact that they are attracted to one another over a distance. It is this attraction over distance which causes the attraction between rubbed objects, where electrons are moved away from their original atoms to reside around atoms of another object. Atoms that have more or less electrons than protons are called ions, A positive ion results when an atom has more protons than electrons. A negative ion results when an atom has more electrons than protons. The process of creating an ion is called ionization. Many elements will become ionized when put in combination with certain other elements. For example, chlorine, Cl, will become a negative ion when paired up with a sodium, Na atom. The sodium Na atom will become a positive ion. Ionization can be caused by electrons, light, and other radiation striking the atom. Smoke detectors use a small amount of radioactive material to ionize atoms in the air. The ions being charged move between charged metal plates, creating a tiny electric current. Smoke particles disrupt the current by attracting the ions, which will in turn trigger the alarm. Electrons tend to repel other electrons over a distance, as do protons other protons. The only reason protons bind together in the nucleus of an atom is because of a much stronger force called the strong nuclear force, which has effect only under very short distances. Because of this attraction and repulsion behavior between individual particles, electrons and protons are said to have opposite electric charges. That is, each electron has a negative charge and each proton a positive charge. In equal numbers within an atom, they counteract each other's presence so that the net charge within the atom is zero. This is why the picture of a carbon atom has 6 electrons to balance the electric charge of the 6 protons in the nucleus. If electrons leave or extra electrons arrive, the atom's net electric charge will be imbalanced, leaving the atom a charged ion, causing it to interact with other particles and other charged atoms nearby. Neutrons are neither attracted to or repelled by electrons, protons, or even other neutrons, and are consequently categorized as having no charge at all. The process of electrons arriving or leaving is exactly what happens when certain combinations of materials are rubbed together. Electrons from atoms of one material are forced by the rubbing of another material to leave their respective atoms and transfer over to the atoms of the other material. In other words, electrons comprise the fluid hypothesized by Benjamin Franklin. The operational definition of a coulomb as the unit of electric charge in terms of force generated between point charges was found to be equal to an excess of deficiency of about 6 quintillion or 250 quadrillion, which is 6 to the 18th power, or about 6 with 18 zeros after it. A single electron has a charge of about 1 divided by that huge number, or 1.6 times 10 to the negative 19 power. Being that 1 electron is the smallest known carrier of electric charge, this last figure of charge for the electron is defined as the elementary charge. The result of an imbalance of this fluid of electrons between objects is called static electricity. It is called static because the displaced electrons tend to remain stationary after being moved from one material to another. In the case of wax and wool, it was determined through further experimentation that electrons in the wool actually transferred to the atoms in the wax, which is exactly the opposite of Franklin's conjecture. In honor of Franklin's designation, the wax's charge being negative and the wool's charge being positive, electrons are said to have a negative charging influence. Thus, an object whose atoms have received a surplus of electrons is said to be negatively charged, while an object whose atoms are lacking electrons is said to be positively charged. As confusing as these designations may seem, by the time the true nature of electric fluid was discovered, Franklin's nomenclature of electric charge was too well established to be easily changed, and so it remains to this day. Thanks for watching.